Today we're going to start chapter 4, which is all about reactions and solutions. But before we can talk about how things dissolve, we have to talk about the structure of water because that is really important. Water is normally our solvent. It's not for everything, but it dissolves a lot of substances. It's called the universal solvent. And the reason for that is because of its polarity. So if you look at the structure of water that I drew, notice that oxygen has four extra electrons, so two sets of lone pairs, and then the hydrogens are kind of bent down into a bent shape. So the area near the oxygen is definitely more negative because oxygen is way more electronegative than hydrogen. It has all those valence electrons on the oxygen, and so that side of the water molecule is going to be more negative than the hydrogen side, which is more positive. And that polarity is really important because when you dissolve a salt or any compound into it, the water is going to surround the particles. And so notice that I have a sodium particle that's positive and a chlorine particle that's negative. And so what happens when water comes to surround them, it's called hydration, when water surrounds the particles, is that water will arrange itself so that only the opposite charges are near each other. So for instance, you see how these water molecules, the oxygen is attracted to the sodium because sodium is positive, and like we just said, the oxygen is extremely negative. Not extremely, it's not a complete negative, but for slight negatives, it's one of the strongest ones. Same thing with the chlorine, except this time it's the hydrogens that are attracted. So when water surrounds itself around the chlorine, it's going to put the hydrogens near the chlorine because chlorine is negative and those hydrogens are slightly positive. And this is called hydration. So when water surrounds these particles, now we've dissolved it into such tiny particles that you can't actually see the particles. And that's why it looks like things disappear. They really just break into really small particles. But it is important that you understand, first of all, how water surrounds something. So you should be able to visualize a salt breaking into positives and negatives, those cations and anions, and the way that the water surrounds them. So oxygen is slightly negative, so it's going to be attracted to the positive particle or the cation. So again, over here, NH4NO3, you're going to need to be able to visualize how that breaks apart. So hopefully you're starting to recognize these polyatomic ions. So this would break into NH4+, which is called ammonium, and this is nitrate. So it's important that you can recognize how those things break apart. The rule for dissolving is called like dissolves like, and this has to do with polarity. So a lot of people think it's based on density, and density does determine which solution or which substance is on top. So when you have that salad dressing at the restaurant and you can see the layer, there's two different layers of salad dressing, you have to shake it up to make them mix together. The one that's less dense is going to be the one that's on top. But polarity actually has more of an effect on whether or not something dissolves. So polar and ionic, which is like an extreme polar something. So polar and ionic can dissolve into something that's also polar, like water, and nonpolar compounds can dissolve in nonpolar solvents. So if you have something that's nonpolar, you're not going to want to use water as a solvent because they're going to be what's called immiscible. It means that it's not able to dissolve. So you have to choose the correct solvent based on the thing that you're trying to dissolve. And that leads us to some of those vocab words that I've already started to use. So solute, make sure you're familiar with the word solute and solvent. Solute is the thing that gets dissolved. It's usually less abundant, and the solvent does the dissolving. And it doesn't have to be a solid into a liquid. It's not always a powder into water. It can be two liquids into each other. It can be a gas into a liquid. It can be a variety of states of matter. But a lot of times we'll do solids into liquids. And we actually need to go back and talk about this word as well. So electrolytes, you hear a lot if you have ever seen a Gatorade commercial. So they're famous for promoting electrolytes that your body needs when you exercise. And it is true, electrolytes are basically anything that can conduct electricity when they're dissolved in water. And so two things have to happen for something to conduct electricity. They have to have charged particles, and those charged particles have to be able to flow. So if you have solid table salt sitting on the table, it's not really going to dissolve. It's not going to conduct electricity because those ions can't flow. They're just kind of stuck next to each other. But once you dissolve them into water, now you've got those charged particles and they're flowing. And that's why it can conduct electricity when the salt is dissolved in water. So first of all, you have to do that hydration where you have the water surround the particles, and then it can conduct electricity. A big part of AP Chemistry is going to be determining the strength of these electrolytes. So notice there we have strong electrolytes, weak electrolytes, and then non-electrolytes. And these have to do with how well they break into ions. So in other words, what percentage of the molecules or the compounds will break into ions. So strong electrolytes are things that when you have a molecule, almost every single molecule breaks into ions. I shouldn't say molecule, I should say compound, because molecules are neutral covalent compounds and they're not going to have charged particles. So compounds, we're talking about ionic compounds, or acids. So remember, strong acids, the definition of strong acids is that they break apart pretty much completely. So for every compound of HNO3, you're going to get charged particles. You're going to get H plus and then the nitrate ion. Same thing for ionic compounds if they're able to dissolve into water. So table salt will almost completely break into ions when you put it into water. And same thing with strong bases. So again, almost 100% of these compounds will separate into ions, and we call them strong electrolytes because there's a lot of electric current that can flow through them because of all those ions. Weak electrolytes are things that still break into ions, but not every compound. And so these are going to be things like weak acids and weak bases, where most of them are going to stay together as the neutral compound, and then a few of them will break into ions. So you still can get a little bit of an electric current, and you can see examples of these. If you take a light bulb and you connect the circuit, you can see that with a strong electrolyte, the light bulb will light up really brightly. With a weak electrolyte, it'll still light up, but it's going to be a dimmer light. And then non-electrolytes are not going to produce ions. So these are things that either don't dissolve, or if they do dissolve, it would be things like sugar, which will dissolve into tiny pieces, but the pieces are not charged. You don't get ions from it, you get covalent compounds or those molecules, and so we call those non-electrolytes. All right, the last thing for today is talking about how we calculate some of these. So we've talked about molarity several times. You need to be familiar with the fact that molarity and concentration are the same thing. Concentration is the thing and molarity is the unit. Molarity is what we measure concentration in. And it's basically just a ratio of how many particles you have compared to how much solution you've put it into. And so if you have a few particles and a lot of solution, that's going to be a dilute solution because you don't have very much of it. If you have a lot of particles and just a little bit of solution, that's going to be concentrated. So dilute and concentrated are relative terms that are describing the ratio of particles to solution. You should be familiar with this by now, that molarity is equal to moles per liter. So you do need to have it in moles and you need to have it in liters if they're asking you for the concentration or if they're asking you for the molarity. Sometimes they'll give you grams and you'll need to convert that to moles. Sometimes they'll give you milliliters and you need to convert that to liters. And I'll go through some of those examples in just a few minutes. And when we talk about preparing solutions, I'll talk about diluting as well, but we've done this equation as well, and we'll talk about what that equation means in a little bit more detail now that you're in AP Chemistry. Okay, let's just go through a few of these examples so you can see how to calculate these. First of all, it says calculate the molarity. It's always good to recognize what unit you're looking for. We have 11.5 grams of solid NaOH, and we have the volume is 1.5 liters. So we have everything we need except that it's in grams, so we're going to set up a little fence, 11.5 grams. We're going to bring grams down, put the moles up here. And if you use the periodic table, it should be about 40 grams per mole for sodium hydroxide. And then we can actually just keep on going on this fence. Let's just keep on going here. So when we do this, notice that the grams will cancel and we'll have moles on top, so we can go ahead and put the volume on the bottom. And now notice that we have moles on top, we have volume on the bottom, and so now we have our unit that we need. So this ends up being 1.92 times 10 to the negative 1. And let's just check our sig figs. It looks like we have 3 for both numbers, so we have 3 sig figs, so that should be good. All right, let's look at the next one. We have 1.56 grams of HCl. And we can use the periodic table to add that up. 36.45 grams per 1 mole. And that gets us moles on top, so now we just need the volume on the bottom. But notice that we have milliliters, so let's convert that to liters, and it should be 0.0268. So just divide by 1,000 to get it into liters. And that gives us 1.60 is the concentration of HCl. I probably should leave all these chemicals on here. It's good to keep those on there so you can keep track of your chemical, but we're not really switching chemicals here, so it's fine. All right, for the next one, it says give the concentration of each type of ion. So first of all, let me just highlight that you can find the ions by looking at the concentration of them up here. I think we talked about this right here. I should have highlighted this section right here. Let's just do an example and let me show you what I mean. So if we have, let's do cobalt nitrate. This is going to dissolve into cobalt 2+. And 2 nitrate ions. So hopefully you can recognize when you see this compound that you have 2 nitrates for every 1 cobalt. You could even write out this dissolving, it's even a reaction, not really a reaction, but it's showing the dissolving as you break apart the particles. But you can show this as the dissolving so you can see the actual ions. And so you see you have 2 nitrate ions for every 1 cobalt. So if you had so many moles of cobalt nitrate and they wanted to know how many ions of nitrate would you have to multiply it by 2, because for every compound it breaks into 2 pieces of NO3, NO3 negative. And you're going to see that quite a bit in AP chemistry where they ask you about part of a compound, and just remember that you'll need to multiply it by the subscript that's in the formula. So going back to this example down here, number 3, it says give the concentration of each type of ion in here. And so actually this is the one that I was doing, is the 0.5 is the molarity of cobalt nitrate. And since you have 1 cobalt ion for every compound, it's going to be the same. So the concentration of cobalt 2+ is going to be 0.5 as the molarity. But if we're talking about nitrate, because you have 2 nitrate ions for every compound, you have to multiply that by 2. And so that's going to be, 1 is going to be the molarity of the nitrate ion. Same thing for the next one. For iron, you would have 1 Fe3+ for every compound, so it would still be 1 is the molarity, but when that breaks apart, because of this little 3 down here, you're going to have to multiply the polyatomic ion's concentration by 3. Let's look at the next one. It says calculate the number of moles of chlorine ions in this concentration. So what we can do is first of all plug in the molarity, plug in the liters to get moles of zinc chloride. And then what we can do is multiply that by 2 because you have 2 chlorine ions per compound. And your final answer for this ends up being 3.5 if you want to try it yourself. 3.5 times 10 to the negative third. All right, just a couple more. We have blood serum here, and it's asking us for the volume. So we've got milligrams here. We can turn that into grams. Then we can turn that into moles, and we've got the molarity, and so we can then plug in moles and molarity into the equation to get the volume. And if you want to try that one, you should end up getting 1.2 times 10 to the negative fourth as your liters. So try these on your own, and if you still can't get them, we can work on these in class. I'm running out of time on my video. I'm down to 1 minute. Okay, let's see this next one. This one is giving us a molarity, and we can use the grams per mole to cancel the moles and get grams per liter, and then we can use the liters to cancel liters. So let me see if I have time to set this one up. Then we can use the molar mass, and this is of K2Cr2O7. Oops, that's per mole. And notice that liters will now cancel, moles will cancel, and we'll end up with grams. And then the last one is just M1V1 equals M2V2. You can plug those in as well. And we'll talk more in detail about how to do those actual dilutions in class.